Hi, and welcome to Quantum 101, a 14-week learning series where we're going to take you from the very beginnings all the way to programming quantum computers. My name is Bob Wold. I'm the CEO and co-founder of Quantum Rings, and it's my honor to be able to welcome you before handing it off to Cora, your instructor, a PhD student from MIT, who will take you through today's lesson. So to get started, first, let's talk about why quantum computing. Imagine a world where some of the most pesky diseases were actually curable because we could do massive amounts of simulations of new drugs in real time. Or a world where we could travel further on EVs that could charge faster and take up less resources from the Earth. A world where we could optimize some of the most complicated transportation and logistics problems to get the goods that are needed to the places they're needed sooner and at less cost. Or a world where we can do other things like financial modeling, training AI algorithms, new forms of cryptography, etc. Well, quantum computing holds the promise to unlock those and many other use cases. And it's estimated that by 2035, quantum computing is going to be creating an estimated $2 trillion in economic value. And so when we look at this, we can sort of understand that there are a lot of problems that are solvable by classical computers today. We have bigger and bigger supercompute clusters that are doing cooler and cooler things. But there's also this set of problems that are solvable by quantum computers, but they just have this nature of being exponentially harder as they grow, and classical computers just don't have an approach to solve them. And that's where most of this value is unlocked. Now, today, we happen to live in this world where we have quantum computers, and they're making tremendous progress, and we're on a trajectory to get there, but most of the problems that we're solving today are still solvable by both classical computers and quantum computers. Now, one of the tricky things is that the way you code classical computers and the way you code quantum computers are fundamentally different. And so that means that we need to go back to the drawing board and learn some new concepts in math and quantum mechanics in order to even have the foundations to start coding for quantum computers. Now, the cool thing is that there's a market for this skill. 60% of Fortune 500 companies are actively exploring or engaging with quantum computing today, and when surveyed, almost all companies that have begun an investment in quantum computing plan to maintain it or increase it. And so if you're here to learn how to create massive value and transform the world, we've got good news. Quantum 101 is a 14-week series that has no prerequisites, requires no prior knowledge, and it's going to teach you all of the math and all of the quantum mechanics required through a series of lecture videos with code notebooks that will take you from the beginning to the end. Now, with that introduction, I'm going to hand it over to my colleague, Cora, who's going to take you through the rest of today's series. So grab a coffee and a notebook, and let's enjoy.
Hi, as Bob said, I'm Cora. I'm a third-year PhD student in Will Oliver's Engineering Quantum Systems group at MIT. Today's lesson is going to cover three main things. One, we're going to be getting started with the Quantum Rings SDK. We're going to set up an account in Quantum Rings and Qubit and then get our coding notebook running. 2, we're going to cover the mathematical prerequisites for the course, which will mainly involve some linear algebra as well as some quantum mechanics notation. 3, we're going to run a simple quantum circuit in Quantum Rings. This is a lot of ground to cover, so let's get started. So the first thing we're going to do is set up the Quantum Rings SDK. So I'm here at the Quantum Rings website, quantumrings.com. So the first thing you'll want to do is come here, and if you already have an account, great. If not, you can make an account. And then once you have your Quantum Rings account, when you log in, it will look something like this. And if you look on the left-hand side here at Manage Keys, you can see your license key, and we'll need this later in order to run our coding notebook. The next thing we'll want to do is, if you haven't already, make an account with Qubit. So just go to qubit.com and make an account. Okay, and then once you're in your Qubit dashboard, you can see this button, Launch Lab. So we're going to launch the lab. And it will bring up a page that looks like this. This is a Jupyter lab where we can have our Jupyter notebooks. Once you get to this point, you'll want to install all the libraries that we need to run our Quantum Rings stuff. So go over to here to environments. We want to add the Quantum Rings environment. So I'll search for rings over here, and you'll see Quantum Rings, and then hit install. and then it may take a while, but it will install the quantum rings environment for you. And then once that's finished installing, you should be good to go. So now the next thing we need to do is get the coding notebook. So what I'm going to do is I'm going to go to GitHub, and I'll find the quantum rings GitHub. And then you'll find a repository called Quantum Summer School. You can click here. And then we want to bring this code into our Qubit lab. So we're going to copy the link, the web URL, and we're going to go back to Qubit. And we're going to go on the side panel here and click Git. And we want to clone a repository. And then we can paste our URL here and clone. And now in our files, we should have the Quantum Summer School repository here. So now I can open up episode 1. So here, there's the same information as before, going to Quantum Rings to log in, but you should have already done that. And then if you want to work with quantum rings locally on your machine, you can do that. But I, throughout this course, will be working in Qubit just to make things a bit easier, and that may also be easier for you as well. So now we have our notebook open, and we want to change our kernel to be the quantum rings one. And now we need to get our key from the Quantum Rings website. So go to your account and find your key under Manage Keys, copy and bring it over. And where it says token, replace that with your key. And where it says name, put your email address. And now we have our activated account. Today, we're going to be going over some foundational math concepts that we're going to be using throughout the course. These are mostly coming from linear algebra. And the things we're going to cover today are vector notation, complex numbers, normalization, Ket or Dirac notation, which is specific to quantum mechanics, inner and outer product, and then unitary and Hermitian matrices. So just as a little bit of a motivation for where we're headed, we need a way to talk about our quantum bits mathematically. So we know that our classical bit in our regular computer, like your laptop or your phone, is just going to be discretely 0 or 1. That's it, only 2 options. But then a quantum bit is not like that. So quantum bit, it could be 0, or it could be 1, or it could also be a superposition of 0 and 1. And we call this quantum bit a qubit for short. And a quantum bit, a qubit, is going to behave unlike anything that you experience in your day-to-day lives. It's going to be governed by the laws of quantum mechanics, and it's very counterintuitive. So when we look at our quantum bit in our quantum computer, we measure it to see its state. We're either going to see 0 or we're going to see 1. We'll never measure anything else. But prior to measurement, it genuinely is in a superposition between 0 and 1. And we're going to explore this more throughout the course. But we need a way mathematically to describe the state of our qubit. And the way that we can do it is with a wave function. And so the wave function is going to encode the probability of certain measurement outcomes. So we know that when we measure our qubit, the possible results are 0 or 1. And then we need a way to basically encode the probability that we would measure 0 and the probability that we would measure 1. So an easy way that we can do this is with a column vector. And we have 2 possible measurement results, so we need 2 probabilities to encode. And so our wave function will look something like this, where the upper component is the contribution of the 0 state, and the second number is the contribution of the 1 state. And we call alpha and beta amplitudes. So we can pretty easily say what our 0 and 1 states are, because the 0 state should be full contribution from the 0 state and no contribution from the 1 state, and vice versa for the 1 state. So our 0 state should be the vector 1, 0, and our 1 state should be the vector 0, 1. Now I could ask you, what if I write down this vector, 1, 1? So this vector shows an equal superposition between 0 and 1, but it's not necessarily physical. And this is because our states 0 and 1 have a norm or length of 1. And it turns out that this is a requirement for quantum state. And we're going to discuss this more later. But basically, if we wanted to have an equal superposition state like this state, we would need to normalize it. So we have our vector 1, 1, and the length of this vector is square root of the first element squared plus the second element squared. This is just like a squared plus b squared equals c squared. So this is root 2. And then our normalized vector would just be 1 over root 2, 1 over root 2. And this is a valid quantum state that will come up a lot throughout the course. So another important thing is that alpha and beta are not necessarily real. So basically alpha and beta can be complex numbers. You can recall that I, the imaginary number, is the square root of -1. And we can have our complex numbers living in a complex plane, where the x-axis is reals and the y-axis is imaginary. So then for any arbitrary point, we have our complex number z, which can be expressed as a sum of a real component and I times the imaginary component. And then this length here will be a, and this length here will be b. Another way that we can express this in terms of complex numbers is in terms of an angle and a length. So you can see here that we have some angle theta, and you could also say, okay, well, this length is r. And how would you express your state in terms of r and theta? You may not have learned this before, and it also may not be intuitively obvious, but we could also express z as r times e to the I theta. And actually, a fun fact, which is also incredibly useful, is that e to the I theta is equal to cosine theta plus I sine theta. So now with that fun fact, we can more easily see the part from before, because now this length is going to be r cosine theta, and this length is going to be r sine theta, and we have that z equals r times cosine theta plus I sine theta. So again, this fact may seem to be coming out of nowhere. How can you have e to the I something and it's just a complex number described in this way? But you can more easily see this if you perform a Taylor expansion. So if you don't know what a Taylor expansion is, that's okay. This is kind of a fun mathematical aside. You don't need to worry about too much. If you know what it is, you might find this interesting. But we know that we can express the function e to the x as 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, and so on. And now we can see what happens when we plug in x equals I theta. So then we would have 1 plus I theta plus 1 over 2 factorial I theta squared plus 1 over 3 factorial I theta cubed. And we need to think about what I raised to different powers is. So if we have I raised to the first power, that's just going to be I. If we square it, we're going to get -1, because I is the square root of -1. If we cube it, then we're just multiplying -1 by I, so we get -I. And then if we multiply by I again, we'll get 1. And then the cycle repeats itself after that as well. You can check. So now we know how to replace our i's with either plus or minus I or plus or minus 1. So now we're going to have e to the I theta equals 1 plus I theta minus 1 over 2 factorial theta squared minus 1 over 3 factorial, or I times, plus 1 over 4 factorial theta to the 4th, and so on. And we can actually group these in terms of purely real and purely imaginary components. So on the one hand, we have 1 minus this plus this, and so on. And then we have the purely imaginary component, which is this. And it actually turns out that this is the Taylor expansion for cosine theta, and this is a Taylor expansion for sine theta. So this is just another way to see how e to the I theta is equal to cosine theta plus I sine theta. So another thing that falls out of this is what is the unit circle in the complex plane? Well, the unit circle is just the circle with radius 1. And so that will be the complex numbers z equals r e to the I theta, where r equals 1. So just e to the I theta for some theta in the real numbers. When we talk about complex numbers, we usually talk about them as encoding some sort of phase. So this comes up a lot in quantum computing, where our wave function coefficients, our amplitudes alpha and beta, like I talked about before, will have some factor of e to the I theta, and we call theta the phase. This will come up a lot. Another thing I think is fun is that we can more intuitively see how I squared equals minus 1. So it's kind of like a bizarre concept. So here we have our complex plane again, and now I would lie here, purely imaginary, and that has an angle of pi over 2. We can also write it in terms of our phases. So I is equal to e to the I pi over 2. And so if I do I squared, then I will just have this times this. And those numbers in the exponent are just going to sum up, and we'll get e to the I pi. So now our new state I squared is going to have an angle of pi, and that will put us over here at minus 1. Just another way to see it. Basically, every time you multiply by e to the I theta, you're just rotating by theta in the complex plane. So another important thing that comes up a lot is complex conjugation. And all that means is just taking the imaginary part of your complex number and flipping the sign. So if your complex number is a plus bi, then your complex conjugate, which is denoted by a star, is going to be a minus bi. And we can think of this visually as well. So if we have our complex plane, and we have our vector, or a number z, then we can draw z star as well. And it will have the same real component, but minus the imaginary component. So the action of complex conjugation is to flip us over the real axis. One of the things that comes out of this very naturally is that when you multiply a number by its complex conjugate, you will always get a real number. So for instance, if z equals r e to the I theta, then z star is going to be r e to the minus I theta. And we can double check on this, because this here is cosine theta plus I sine theta, and this here is going to be cosine of minus theta plus I sine minus theta. And cosine of minus x is x, so this is just going to be cosine theta. But sine will flip in sine, so this will be I sine theta. So you can see that this satisfies being a complex conjugate. And now if we multiply z by z star, then we're just going to get r squared, e to the I theta, e to the minus I theta. Those cancel out, and we'll just be left with r squared. So now we're equipped to discuss qubit states. We said before that we could choose 1, 0 and 0, 1 to represent our 0 and 1 states. And we can write this in a different notation, which is called Bloch notation, or Ket notation, or Dirac notation, named after Paul Dirac. And what that looks like is we just have a straight line and an angle bracket. This is our Ket. So this is the 0 state, and this is the 1 state. So why would we want to do this? It seems like a column vector is perfectly fine, right? But as we get to more complicated quantum systems, so for instance, if we have a system of many qubits, then we're going to have a column vector with exponentially many entries. So this is just a compact notation for us to use. So now we can also write down an arbitrary quantum state. Physicists love to use the Greek letter psi for wave functions. So we're going to have our arbitrary quantum state be psi. And again, it's just going to have our coefficients alpha and beta from before. And these are our complex amplitudes. So alpha and beta are complex numbers. A fact that we can use is Born's rule. And Born's rule tells us the probability of measuring 0 is alpha squared. And this is alpha times alpha star. And then similarly, the probability of measuring 1 is beta squared. 0 and 1 are the only possible measurement results that we can get. And there's a 100% chance that we're going to measure something. And they're also mutually exclusive. So if you measure 0, you can't have possibly measured 1, and vice versa. So what that tells us is the probability of measuring 0 plus the probability of measuring 1 better equal 1, because there's a 100% chance we measure something. So that gives us our condition alpha squared plus beta squared equals 1. And this is our normalization condition. So remember how I said before that this state 1, 1 was unphysical? This is why. Because if we had this state, then that would say that the probability of measuring 0 is 1, and the probability of measuring 1 is also 1. And that just is not possible. So this is not allowed. We need our states to be normalized. So we have our ket psi. In the same way we can take a complex number and take its complex conjugate, we can also take a ket and take its adjoint. So it's kind of like complex conjugation, but for a vector. So then we're going to have our bras, which is just a flipped version of a ket. And this is the conjugate transpose of psi. So conjugate means take the complex conjugate of all the elements in the vector. And then transpose means to flip across the diagonal, so a column vector would become a row vector. And the notation that we use for this is a dagger. And you can also see why this is called Bloch notation, because if you put something like this together, now you have a bra and a ket. So what does psi look like, or the bra psi? So if it's our ket psi is alpha beta, then if we take the complex conjugate, we'll have alpha star beta star. And if we take the transpose of that, we'll get a row vector. And this is our bra psi. So what can we do with these type of things? We can do a lot of fun mathematical operations. One example is the inner product. You may have heard of something called the dot product. So you can take the dot product of two vectors. This is just a more generalized version of the dot product. So if we have our ket psi, and we have phi, which can be gamma delta, then the inner product of phi and psi tells us how much psi and phi overlap, in the same way that the dot product of two vectors gives us a notion of how much they overlap. So more specifically, with our case, we would have the bra phi times the ket psi, and then we would just perform normal matrix multiplication in this case. So we'd end up having gamma star alpha plus delta star beta. Now we can think about some specific cases. For instance, we can have the inner product of 0 with itself. If we write that out, it will look like this, and we get 1. That makes sense. That state should 100% overlap with itself. We could also consider the inner product of 0 and 1, and in that case, we would get this, and that would be 0. That also makes sense. 0 and 1 are complete opposites, so they should have nothing in common, no overlap. And then we can also consider the inner product of an arbitrary state with itself. And because our states are normalized, that's going to be 1. So this is our normalization condition cropping up again, that alpha squared plus beta squared needs to be equal to 1. The inner product also gives you a notion of the probability of measuring something. It tells you the probability of measuring one state when you're in the other. The way we can do that is by taking the inner product squared. So for example, this is going to tell us the probability of measuring 0 if we are in the state psi. And this is just going to be 0 psi times 0 psi star. And this is going to be 1, 0, alpha, beta. So this is going to be alpha, and this will be alpha star. So this is magnitude of alpha squared. And we said before that the coefficient alpha alpha squared would tell us the probability of measuring 0. So this is all adding up. So our bras and kets live in a Hilbert space, which is a vector space with an inner product operation. We don't need to know too much about that, but basically we have some space which contains all possible states, and it also contains all of their adjoints, and we can perform the inner product operation. So for example, psi equals alpha beta lives in a two-dimensional Hilbert space, and that space is spanned by the states 0 and 1. There's also something called the outer product, which will come up later, so I'll mention it here now. And we just flip the order of the bras and the kets. So we can take the outer product of phi and psi, for instance. And we would just follow normal matrix multiplication for this. We can explore this more another time. So now let's return back to our arbitrary quantum state. And we know that we have our normalization condition, which is that alpha squared plus beta squared needs to be 1. And we know that alpha and beta are complex numbers, but there's no reason why we couldn't choose alpha to be real, because if alpha was complex, we could just pull that complex phase out of both of the coefficients, and nothing physical would change at all. That would just be called a global phase, and we'll ignore it. So basically we have 4 degrees of freedom with 2 constraints, because each complex number has 2 degrees of freedom. We're going to choose alpha equals cosine theta over 2, and magnitude of beta needs to be sine theta over 2 then, such that alpha squared plus beta squared can be 1. But what we can do is we can have any arbitrary phase. So let's say e to the I phi on beta. And we can picture this on the surface of a sphere. So there's two cases that we know really well. So 0 is the case where alpha equals 1 and beta equals 0, which can be satisfied by theta equals 0, and phi can be anything. And then we also have our one state, which is alpha equals 0, beta equals 1. And this can be realized when theta equals pi or phi equals 0. So we can draw this on a sphere. So now we have our arbitrary quantum state, which points to some point on the surface of the sphere. This is our state psi. Then the angle theta would be the polar angle down from the z-axis. And we can envision ourselves projecting psi down to the xy plane. And if we do that, we'll get a vector like this. And phi is the azimuthal angle from the x-axis. And this is how we can envision our arbitrary quantum state on the surface of a sphere. We'll come back to look at this in more detail later, but I will point out two other really important states on the sphere. So one is pointing along the x-axis, where we call this the plus state. And you can check for yourself that this is 1 over root 2 times the 0 state plus 1 over root 2 times the 1 state. And you can also check for yourself that if we do the same thing on the minus x-axis, we would get what we call the minus state, which is 1 over root 2, 0 minus 1 over root 2, 1. So the last thing I want to talk about today is operators. And an operator is how we do stuff to our qubits. So basically manipulating them or measuring them. And an operator is some mathematical object which takes you from one quantum state to another quantum state. And we know that our states are basically just column vectors, so that would make our operators matrices. So for instance, acting on a column vector gives you another column vector. And if we were to write this in bracket notation, we would have some operator, which we usually denote with a hat, acting on our state psi gives us some other state psi prime. So we can think about the properties that we would want for our operators. The first thing is that if A transforms one qubit state to another, then that other state would also need to be normalized. Let's say A psi equals psi prime, and these are both valid quantum states. Then we know that psi inner product with itself will be 1, but we also need to preserve the norm of psi prime. And so what would be good is if A preserved the norm of a vector when it transformed it. And we can think about the condition for this to be true. We can also write out the inner product of psi prime with itself as an operator A acting on psi, the dagger of that, and then A acting on psi. When we take the dagger, it flips the order of the two things and also takes the dagger of it, so our psi will become a bra and a dagger, a psi. And what we really need is we need this to be the identity matrix. So then this would be psi psi, which is 1. Because if it's any other arbitrary matrix, then this may not work for every single qubit state psi. So we call this a unitary matrix. And the condition for this is that A dagger A equals A dagger equals the identity matrix, or in other words, A dagger is the inverse of A. So another thing that we may want, or something that we definitely want, is all of our operators are going to correspond to physical observables. So for example, the position of an electron, the state of a qubit, the energy of a photon. In quantum mechanics, all operators correspond to something physical that you could observe. And the result of measuring a physical observable is always real. You will never measure the energy of a photon to be imaginary. Another thing that we can know is that the possible measurement results for an observable are its eigenvalues. So we will talk more about eigenvalues and eigenvectors in a later episode when it's more important. But just as a reminder, if you haven't seen it before, it's when an operator or a matrix acts on a vector and you get back that vector scaled by some factor. So this is a scalar factor, which we call the eigenvalue. And this is our eigenvector. And we want our operators to have real eigenvalues only. And the type of matrices that satisfy this are Hermitian matrices, which is where A dagger equals A. So we can prove this pretty easily. So suppose that psi is an eigenvector of A hat with eigenvalue A. Then we can imagine taking a bra and pre-multiplying. And a scalar factor can just pass through. So this would just be A psi psi, but this is going to be 1. So it's just A. And we can take the dagger of this entire thing, or I guess the complex conjugate. And this would give us A star, because A, as far as we know, is a complex number. But this would equal, we just flip the order of everything and take the dagger. But A equals A dagger. So what we've shown is that A is its own complex conjugate, or in other words, A must be real. Okay, now that we've covered all of the math, we're going to come back to the notebook very briefly. So I just want to show you how we can quickly run a small, simple quantum circuit using quantum rings. So the first thing that we can do, once we've already initialized our account, is we can import the libraries that we need. And then in this chunk of code here, we're creating a quantum register, which will have 1 quantum bit, a classical register, which will have 1 classical bit, and we're making a quantum circuit which has 1 quantum bit and 1 classical bit. So we're going to apply a gate to the qubit, and then we're going to measure it, and then we can run this. So we defined our backend before. It was this scarlet quantum rings, and we're going to run our quantum circuit, and we want to run it 512 times. So if you'll recall, we can only ever measure 0 or 1, but before that, our qubit is in a superposition of 0 and 1. So we're going to get some probability distribution of 0 and 1. So we want to do many measurements. So we can run this and get our result, and then finally we can print out our results. So we measured 0 276 times and 1 236 times. We covered a lot today, including getting started with quantum rings, going over the basics of linear algebra, complex numbers, and quantum mechanics notation, and running our very first quantum circuit using quantum rings. Today's video serves as a foundation for the rest of the series. We will continue to use this math and notation throughout the course, and we will keep building up our understanding of quantum computing. Next week, we will explore single qubit measurement and gates. I'll see you then.